Hello there guys, how's it going? Mike coming back at you here with another video on Calculus 1. In the previous video, we looked at some sample problems involving the mean value theorem. We saw that we have to verify that the hypotheses of the theorem are satisfied, and then once they are, we went through that fairly short process to actually solve the problem as given. In this video, we are going to introduce ourselves into the other major topic that you would see in any Calculus 1 course, that is anti-differentiation or indefinite integration. So, what have we done up until so far in this course? If you were given a function little f of x, right here, you would be asked to differentiate this guy, and I'll put a capital D here to stand for the differentiation, and come up with f prime of x, little f prime of x. Well, what we do in anti-differentiation, or indefinite integration, as the name suggests, we are going to work in the opposite way. You'll be given a function little f of x, and you have to find this function capital F, such that when you take the derivative of capital F of x, you get little f of x. So we want to find the function capital F such that capital F prime is equal to little f. And we call this function capital F the antiderivative of little f of x, or we call it the indefinite integral of f. Now, you'll also hear me use just the integral of little f, so I'm using these things interchangeably here. So what we're going to talk about in this video are the major properties and major rules of indefinite integration or anti-differentiation. Before we get into those properties, note the symbology that we are using here. To say or to talk about the indefinite integral of a function f of x, we use this sign here. It looks like a very long stretched out S. And then accompanied with that is this dx thing here. The letter that follows the d there should always be the same as the variable that you have in your function. So since this is a function of x, we should have a dx. If you had a function of the variable t, you would see a dt. There is a larger role that this thing plays in more advanced math classes, but obviously that is not in the scope of our course, so we're not concerned with it. But just know that the letter following the D should always match the letter that is in your variable. And what this is really saying is integrate with respect to this variable, and this variable is the variable you have in your function. So we have two functions, little f of x and little g of x. The antiderivative or indefinite integral of little f of x is capital F, integral of little g is capital G, and suppose that k is some constant. Property number 1 here just says that the integral of the difference or sum of two functions is equal to the difference or sum of the integrals of the individual functions. Integral of little f plus or minus little g dx is equal to capital F plus or minus capital G, and that's just the difference or sum of the individual integrals. That should look familiar. We've seen the same kind of thing done in limits and the same kind of thing done in differentiation as well. Number 2 should also look very familiar here. The integral of a function times a constant. The integral of k times your function f of x dx is equal to k times capital F of x, which is equal to k times the integral of f of x dx. So what this is saying is that if you have your function of x and you're multiplying it by some constant, you can pull that constant outside of the integral sign. Now we get into taking the integrals, the integral or the antiderivative of some specific kinds of functions. Number 3, what is the integral of a constant? The integral of a constant k is k times x plus c. Now, a note on these plus c's, once we get through the rest of all of our rules here, we'll come back to why we're seeing these plus c's. Number 4, how do you take the integral of x raised to the nth power? Well, provided that your exponent is not -1, then you use this following rule. The integral of x to the n dx is x to the n plus 1 all over n plus 1 and then plus c. If your exponent is -1, then x to the -1 is 1 over x, and the integral of 1 over x dx is stated in number 5. The integral of 1 over x dx is the natural log of the absolute value of x plus c. Now, why do we have the absolute value signs on the x? We do this just so that we can incorporate more inputs into this natural log function. By taking the natural log of the absolute value of x, we can also plug in any x values that are strictly negative. 6. What's the integral of the general exponential function b to the x? The integral of b to the x dx is b to the x divided by the natural log of b plus c. We have our special case of b to the x, e to the x. So we get the integral of e to the x dx is e to the x plus c. This is the nicest function you can possibly have. We saw that if you differentiate e to the x, you just get e to the x. Well, if you take the antiderivative or the integral of e to the x, you also get e to the x. Now we get into integrals of trig functions. The integral of sine x is minus the cosine of x plus c. 9, the integral of cosine x dx is going to be sine of x plus c. Now the next few results are related to derivatives that we saw a bit earlier on in this course. The integral of secant squared x dx is tan x plus c. The integral of secant x times tan x dx is equal to secant x plus c. The integral of minus cosecant squared x dx is cotangent x plus c. And then the integral of minus cosecant x cotangent x dx is equal to cosecant x plus c. So those are numbers 10 through 13. Now we finish up these last 3 where what we're finding is the integral of the derivative of an inverse trig function. We saw that the derivative of arcsine x was 1 over the square root of 1 minus x squared. That means that the integral of 1 over the square root of 1 minus x squared is arcsine x plus c. 15. Integral of -1 over the square root of 1 minus x squared dx is equal to arc cosine x plus c. We're going to see later on in this video, when we go through some sample problems, that is possible based on seeing something like these guys, it's possible to come up with two separate answers which are both completely correct when you find the indefinite integral of a given function. And then lastly, 16, the integral of 1 over 1 plus x squared dx is equal to arctan x plus c. So those are the basic anti-differentiation / indefinite integration properties and rules that you will need to know. Now, before I said we're going to come back to these plus c's that are showing up at the end of each of these guys. Well, suppose I know that given a function f of x, the antiderivative is capital F of x. So I know that if I differentiate capital F, I'm going to get small f. Well, the thing is, this is just one possible function that would make this true. If I were to look at capital F of x plus any constant whatsoever, if I were to differentiate this thing, would I get little f of x? Well, I know that when I differentiate the capital F of x, that gets me to little f, because we already knew this part, plus what I get when I take the derivative of a constant. But when I take the derivative of a constant, what do I get? I get 0. So, yes. So, this guy right here, f of x plus c, this actually gives us the family of antiderivatives of this function, little f of x. And when you're doing indefinite integration, you want to write the entire family of antiderivatives. You want to include that plus c. You need to include that plus c. So do not forget that plus c on the end of any indefinite integral. Otherwise, you'll get a point taken off because there are multiple correct answers. So we are going to do some sample problems now. We're going to use these rules and see what are the indefinite integrals of some of these basic kinds of things. So, first up here, I have the integral of 3 plus 6x squared minus x to the 1/2 minus 5 raised to the power x. Sorry about that there. So we have the difference or sum of multiple terms here. We know from our first property that we can take those, we can take this whole thing and we can break it up at the plus or minus signs. So we can work with these things separately. The integral of the 3 is just going to give me 3x. That's just the integral of a constant. The integral of the 6x squared. Now I have a 6 times my x squared, so I can just take the integral of the x squared piece and then multiply that 6 back in at the end. The integral of the x squared piece, going back to our properties here, looking specifically at number 4, if n is 2, the integral of x squared is x to the 3rd all over 3. And then we multiply that 6 back in. And that gives me 6x cubed over 3, or we get a 2x cubed. Now I have an x to the 1/2. Again, this is x raised to some power that's not -1. So we are good. We're going to use that same rule. So the integral of x to the 1/2 is going to be x to the 1 plus 1/2, or 3/2, divided by 1 plus 1/2, or 3/2. But dividing by a fraction is the same thing as multiplying by the reciprocal of that fraction. So what we get here, equivalently, is 2/3 times x raised to the power 3/2. And then we have minus 5 raised to the power x. This is going back to the integral of an exponential function, property number 6 here. Our base value in this case is 5. So making that substitution, we get 5 to the x divided by the natural log of 5. 5 to the x divided by the natural log of 5 plus c. This is one of those examples where I say it's hard for us to keep track of differentiating and anti-differentiating there. And then we have our plus c at the end. Now, you may have written a plus c for each of these 4 terms. That's okay, technically, but these are all just unknown constants, so let's just write one big unknown constant at the end. So just put 1 plus c at the end of that whole thing. Moving on to our second one, the integral of -4 over x minus sine x plus secant x times tan x dx. Looking at the first term there, we have a -4 divided by x. I can pull that -4 out front and just have the integral of the 1 over x piece. The integral of 1 over x we saw is the natural log of the absolute value of x. So multiplying that -4 back, we get -4 times the natural log of the absolute value of x. Now we come to minus the integral of sine x. Well, we saw that the integral of sine x was minus the cosine of x. So we're going to have minus the cosine of x, or plus cosine x, plus the integral of secant x times tan x. The integral of secant x times tan x is one of our nice basic rules here, number 11. That gives us secant x. And then we have our plus c at the end. Third one here, 3 over 4 plus 4x squared plus 9e to the x plus plus cosecant squared x. We're going to find the integral of this whole thing here. Now this first term may look a little bit odd, so allow me to rewrite it like this, and then maybe you'll see what's actually happening here. I can pull a 3 out front on the top, and then each of the 2 bottom terms contains a factor of 4. So I have then 1 over 1 plus x squared. And that whole thing is being multiplied by 3/4. So that should make it a little bit easier to see what we're actually working with here. The integral of 1 over 1 plus x squared is the arctangent of x. So we have 3/4 times arctan x plus the integral of 9 times e to the x. The 9 is a multiplicative constant. We can pull that out front and multiply it back in at the end. The integral of e to the x is just e to the x. So we get plus 9 times e to the x. And then we saw that the integral of minus cosecant squared x is positive cotangent x. If we multiply both sides, or divide both sides, whichever one you choose, by a -1, you find that the integral of plus cosecant squared x, like we have here in our problem, is equal to minus the cotangent of x. So we have minus the cotangent of x, and then we have our plus c at the end. And one more example here, minus 11 cosine x minus 3 cosecant x cotangent x minus 8 divided by the square root of 1 minus x squared. If we integrate the first term here, we have negative 11 times the integral of cosine x. Integral of cosine x is sine x. Minus 3 times the integral of cosecant x times cotangent x. That's going to be a minus cosecant x. So the minus and the minus multiply out to be plus. And then minus 8 times the integral of 1 over the square root of 1 minus x squared. Now this is where we could possibly have two separate answers. If you include the minus sign in your integral, and you have the integral of minus 1 over the square root of 1 minus x squared, and you have a plus on the outside, you would get 8 times the arc cosine of x plus c, and that'd be a plus 8. If you kept the minus sign outside of your integral, though, and you just did minus 8 times the integral of 1 over the square root of 1 minus x squared, you're going to get minus 8 times the arc sine of x. But the first two terms are always the same, just a little bit of variance on that third term. And as always, we have plus c's. So these are a few practice problems to help get your feet wet with anti-differentiating or performing the indefinite integral of a given function. In the next video, we are going to do some more practice with these guys. We're going to see some more of these problems. And then we're also going to look at things known as IVPs. If you have a question or comment, be sure to drop them in the comment section below. Otherwise, until the next video, folks, take it easy.